Question 1 from the free response. Now, they're looking at home run hitters from the 1900s to the 2000s. If you read the problem, they give you all this data here. We want to make a side-by-side box plot. Okay, so let's start with that. Well, what I would do is make a number line. So the lowest number is about 9, highest number is 70, and that includes both graphs. So I would maybe start with a rough number line that's evenly spaced from, say, 0 to 80. So something like this, and I'm going to start with the 1900s, and we're just going to make a box plot. So it's going to look like this. The median is at, say, 46, and Q3 is at 54, so that might be like right there. 35, like this. So that's Q1, Q3, and the median. And then 22, so it just comes down here to that. And then the highest is 60. So that is for the 1900s. Okay, let's do another one just right underneath it using the same scale for the 2000s. So then letter B is, can we describe these two? It's like a compare and contrast between these two graphs. So you could say that the median for the 1900s is higher than the 2000s, and they're both roughly symmetric, but the 2000 has a much more variance in it, which tends to indicate that it's got a higher standard deviation. We can't really say, based on the two graphs, which one is better, but we can say that the 1900s was much more consistent in the home runs. Anyway, stuff like that. That's what you would say for the next one. That's letter B. And then letter C says, let's see, what test of significance would you use? Well, since we have the mean and the standard deviation, and they're two distinct groups that we're comparing, so it would be like a difference, right? So you would do a two-sample t-test for means. That would be the type of test we would do. Okay, there it is. Two-sample t-test for difference of means. And then the last one is the conditions. Remember, we're going to look for random, normal, independent, right? Random, normal, independent. So we've done this so many times. So, is it random? It says it in the problem. Is it normal? Well, the normal part is a little tricky. If we had 30 or more, we could say central limit theorem. But we don't. We only have 12 and 15. That's the number in our sample. But luckily we have these box plots, and there doesn't seem to be any dramatic skewness or outliers, so normal is okay. In independent, we could say that each home run hitter probably has no effect on any other hitter, something like that. And from our population, there's over 150 baseball players that we could choose from. That's independent. There you go. If you've been doing that, you should be good to go. Okay, let's look at the next one. Okay, on this one, now if you read the question, they're going to take a survey, and what is the problem with this? Let's see. Explain the sampling method may introduce biased results. Do you think it would over or underestimate the proportion? How should the school board have selected their sample to avoid bias? Okay, so there's lots of problems here because this is a convenient sample. They just asked the first 250 people that show up. Secondly, these people that show up probably have some connection to the school, students that go to the school, or friends and family, the whole thing. Also, these people that come to the school event probably have some strong opinions about education in general, rather than the average person on the street, which brings us to, that's what you should do. You should be just asking a random individual. Elderly people, people that are out of work, people that don't go to the games, just because everybody's going to be paying this increase in taxes, you should have a cross-section of the entire community. You're probably going to get just parents when you ask these surveys. So you're going to get people from, say, I don't know, 35 to 55, maybe some grandparents. Maybe you should be asking lots and lots of different people. Okay. Why is the question bias? Well, in the beginning, it talks about technology for students greatly increase academic achievement. Who wouldn't want that? You're kind of skewing the answer to say yes. So it's kind of hard to say no to that. Okay. Now, what you should do is when you write a question like this, you should really just stick with the facts. Just make it simple. Something like, do you support an increase in the technological education plan for our school? Yes or no? That's it. So, that's how you can avoid bias. Alright, let's go to the next one. Okay, I don't think that these problems are too bad. We just have this two-way table, eye color versus hair color. What is the probability that a person chosen at random from the sample with half brown hair? We take all the people, let's see, people that have brown hair out of the entire group. We're just picking someone at random from this group. So, we should say it is going to be 286 out of 592, which gives us 0.483. Now, the next one says, what's the probability that a person chosen at random from the sample who has blue eyes? So given that they have blue eyes, all right, so out of all the people that have blue eyes, what's the probability that they have brown hair? So we go over here. This is our group. All the people with blue eyes. How many of them have brown hair? 84. So we're going to do 84 out of 215. And see what we get. And that number is 0.39. Now, based on your answers to A and B, are the hair color and eye color independent? Yes, they are independent because this proportion or probability is different than this one. If they're different, then they are independent. In other words, it wouldn't matter if they had blue eyes. You would get the same proportion of people with brown hair, whether they had blue eyes or not. So, again, they are independent because these two numbers are not the same. Okay, let's go to the next one. Okay, on this one, state of the economy. So we took a look at some people. Let's see. 484 were sampled. 257 said that they felt that it was optimistic. Okay, let's do a test of significance. So this is going to be a z-test for proportions. They either say the economy is doing better or they don't, right? So it's a z-test for proportion. Let's write that down. So now we have to establish our parameter. So we're going to say P is equal to the true proportion of people in the population that feel that the economy is getting better. So I'm just going to do it this way. Let P equal the true proportion of people that are optimistic about the economy. Okay, we could state the problem. We want to find out, does the population have a good, optimistic view of the economy? That's what we're trying to figure out. We're doing a z-test for proportion. So we're going to establish our parameter. Let P equal the true proportion of people that feel good about the economy. Okay, now, we, of course, have to do random, normal, independent, random, normal, and independent. So random wasn't a random sample. Normal is, well, we got to get our proportion. So the sample proportion, that's p hat, is going to be 257 over 484. There it is. And it comes out to be right around 0.53. So that's equal to 0.53. Okay. So we're going to say if we take 0.53 and multiply it by 484, do we get a number that's bigger than 10? If we take 0.47 and multiply it by 484, do we get a number that's bigger than 10? That's for proportions. So that's, and then independent, we could say the 10% rule. We're going to assume that there's over 4,840 people in this population that we're sampling. We could also say that one person's opinion of the economy has no effect on any other person's opinion. Okay. Now, let's do the math part. Oh, I almost forgot about the null hypothesis and the alternative hypothesis. So we're just going to say that we're going to assume no change, that the opinion is 50% of the people feel good about the economy, versus we think that it's more than 50%. Okay, so how do we set this thing up? Well, it's going to be like this. The thing that we're interested in is 0.5 minus what we got, which was 0.53, our sample proportion. And then we're going to divide that by the standard deviation. So let's figure out what the standard deviation is. Well, we need the standard deviation, the proportion for the population, but we don't have that. So what do we use? We say 0.5, just assume 0.5 over 484. Okay? So, but we can always, we use that null hypothesis proportion to figure out our standard deviation. And there it is. And when you do the math, you should get 1.32. What does that tell us? Where 1.32 standard deviation is above the normal, the middle of the graph. So what do we do with that? Well, we're going to do normal CDF and plug this number in. Since we're looking for something bigger than 0.5, we're going to subtract it from 1, and you should get a p-value of 0.0934. There it is. That's the p-value. So, what does that tell us? Well, our conclusion is going to be we are going to reject, no we're not, we have an alpha level of 0.05. This is bigger than 0.05. So we're going to fail to reject the null hypothesis. We just don't have enough evidence to say that more than 50% of the population feels good about the economy. Okay. Then letter B says, can you interpret the p-value? So the way this works is you say, well, assuming that our population proportion is 50%, in other words, 50% of the people feel good about the economy, if that's true, if our null hypothesis is true, we would get a result this big 9% of the time. That's what interpreting the p-value is. Given that this is true, we would get this result 9% of the time. Okay, and you got to write that up. There you go.